All right, let's look at part C. This is a little bit more non-trivial problem. In the previous part, we were given exactly what the ln 1 minus x squared corresponds to, but in this problem, we're not given anything. I would just go in the direction of like taking the derivative of ln 1 minus 1 plus x squared with the expectation of getting a fraction. Because if you look at f prime of x, it's 2x over 1 plus x squared. So if I know the power series expansion of 1 over 1 plus x squared, I'm done. Because I'm just going to multiply by 2x, and that would be the power series representation of the derivative of f. And if I integrate the derivative, I can go back to the f and get the power series representation. So for that purpose, why don't we look at the power series representation of this term here? Because this already follows the form a minus r, a over 1 minus r, right? That's equal to a r to the n, the geometric series, right? So I can rewrite this 1 over 1 minus minus x squared, right? So this becomes r, and a equals 1. So I can go ahead and rewrite this as like 2x series, let's see, a is 1, r is negative x squared to the power of n. Okay? And I can so like separate negative part of the parentheses from the others. So 2x negative 1 to the n, x to the 2n. And as you see that, I'm multiplying everything by 2x. So when you expand the power series, it's all x related, and then I'm multiplying that by x. Let's just do that. So I can immediately multiply everything term by term by x, okay? And so x to the 2n times x becomes x to the 2n plus 1. Okay, so this is the PowerPoint representation of the derivative of f, which is f prime. So if I want to get the PowerPoint representation of the original function I started with, I'm going to integrate this power series term by term in the next line. All right, so I just copied the description of f prime, the power series representation I came up with. And the antiderivative of f prime is exactly equal to f of x, okay? But obviously I'm going to have an integration constant coming along, and that's equal to, that's going to be added later on. I have to determine that as well, okay? But this is sort of like the relationship between f and f prime, and writing ln of x squared plus 1 in terms of the power series of f prime, okay? So here, let me just write that down. This is 2 integral the infinite series. Okay, I'm going to do like term by term integration. And I'm going to add a constant here. Okay. And that is 2 minus 1 to the power of n, by the way. Okay, minus 1 to the power of n, x to the 2n plus 2 divided by 2n plus 2. So this should be equal to ln x squared plus 1. Okay, ln x squared plus 1. Okay. And who is c here? Well, to find c, why don't you plug in x equals 0? Okay. If you plug in x equals 0, the left-hand side is ln 1, which is 0. And then this is still c. And then n starts from 0 here. If you expand this out and plug in all the values here, you will see that okay, x equals 0 takes you to c equals 0. Okay, check back and so like convince yourself that you have the same representation here. Okay, and one final shot that you can check by yourself. This is already a very long video anyway for this question. Is the convergency of the power series. Okay, so this is 2 negative 1 to the n divided by 2n plus 2 times x to the power of 2n plus 2. All right, we already know from here that x is supposed to be less than 1. So what you need to check is that this already carries forward here, so that I have -1, x, and 1 for the interval of convergency. But you have to convince yourself that you can add the equality signs here, because if you include the endpoints, so this term here is going to be always 1 because it comes with an even power, and it's an alternating series for both -1 and 1, and you can use the alternating series test with an being 1 over 2n plus 2. Okay, and it's a decreasing sequence, and it goes to 0, and all two conditions of the alternating series test are satisfied, so you can actually include the equality signs here, so that the interval of convergency would be -1 and 1. Okay, so going back to the original problem here, so you can actually add -1 and 1 here, so this would be the interval of convergence for ln 1 plus x squared. Again, this was sort of like a relatively non-trivial question, because we first took the derivative of the given function to be able to use the given series here. Okay. In the other questions, though, the partial fraction is provided to you, or how you get ln 1 minus x squared out of integrating two fractions. But in the third one, nothing is provided to us, so we had to guess how to start the problem. All right, this ends the video. Thanks for watching. I'll see you in another video.